In this video, I'll describe some different components of representational systems. I'll cover verifiability, unambiguous representations, canonical form, inference and variables, and expressiveness. Meaning representations should ideally be verifiable and unambiguous. Similar expressions, despite their syntactic differences, should map to the same canonical form, and systems should be able to infer common sense conclusions from meaning representations. Meaning representations should also be expressive enough to handle a wide range of topics. Verifiability refers to the capacity to determine whether the meaning of an input phrase or sentence can be verified by the world as we know it. Meaning representations should reflect real-world facts, and computational systems often seek to verify these facts using external knowledge bases, for example, large structured sources like Wikipedia. For example, given the sentence or proposition, Giordano's serves deep dish pizza, we would want to represent the underlying meaning in such a way that we could verify its truthfulness. We might choose to do this by, for example, parameterizing the word serves with the restaurant name and the name of the food, because this would produce a generalizable form that we could also use with other similar sentences. Then we could check some sort of knowledge base where we had access to a bunch of restaurant names and the names of foods that they serve, and check to see if the information was correct. Meaning representations should also be free of ambiguity. Although we've talked a lot so far about syntactic ambiguity, semantic ambiguity can also be a very common issue. For example, sarcastic phrases are ambiguous because they typically mean the opposite of what is expressed in literal terms. Idioms and metaphors communicate meaning that is analogous in an abstract sense, but not literally the same as what is expressed. And hyperbole communicates information that is less serious than its exaggerated literal terms. Basically, individual expressions can communicate underlying meaning that differs depending on the circumstance. I might say, I love waiting in line at the DMV, and in fact mean the exact opposite, whereas there is possibly someone out there who could utter the same thing and truly mean it in the literal sense. In the context of this module on meaning representations, we'll mainly ignore ambiguities arising from figurative language because that's a whole very interesting but also very complex area, and that still leaves us with plenty of other semantic ambiguities to unpack. To resolve semantic ambiguities, systems need to be able to select which from a set of possible interpretations is most correct given the current context. For example, if I'm Godzilla and I say, let's eat somewhere near SEO, I might be talking about eating some building near the Science and Engineering Offices building. But if I'm hanging out with some of the other faculty and say the same thing, I'm probably talking about eating at a restaurant near the building. Now, I will note that what I'm talking about here is different from vagueness. Vagueness just means that something is underspecified, but it generally can't be interpreted in separate ways. It's actually useful for meaning representations to maintain a certain level of vagueness since it makes them more easily generalizable. So, an unambiguous sentence is one that cannot be mapped to multiple meaning representations. Multiple sentences that mean nearly the same thing actually all should be mapped to the same meaning representation, and that single representation for multiple sentences is referred to as a canonical form. Basically, if we saw all of the sentences here, we'd probably want to map them all to something like we saw previously, where we have the word serves parameterized by Giordano's and deep dish pizza. This makes it much easier to focus on the underlying semantics rather than little word or syntax differences. There are a number of ways that we can reduce sentences to canonical form, including by exploiting grammatical regularities or even by leveraging word embeddings. Although we've talked about verifiability and needing to be able to confirm what is said with what the actual facts are in some knowledge base, it's impossible for a knowledge base to be able to comprehensively cover everything that can be known about the world. Because of this, computational systems also need to be able to perform common sense reasoning and draw inferences based on meaning representations. For example, we might not have an explicit fact anywhere that says that people who like deep dish pizza would want to eat at Giordano's, But as humans, we can guess that if Giordano's has deep dish pizza, then deep dish pizza lovers will probably want to try the restaurant. In more general terms, inference is a system's ability to draw conclusions based on background knowledge and input meaning representations. Systems should be able to draw these conclusions to verify the truth of propositions that aren't explicitly present in the knowledge base, but that are logically derivable from the propositions that are present. Variables help the system during this process because they allow it to build propositions without requiring a specific instance of something. For example, you could have serves parameterized by X in deep dish pizza, and that just means that some place X serves deep dish pizza. It could then be matched by any values that would result in a truthful proposition. Finally, a system's expressive power refers to its ability to represent a wide range of ideas. Meaning representations should be expressive enough to handle many different topics without sacrificing things like verifiability. So this video has introduced some necessary terms and requirements for meaning representation systems. In the next few videos, we'll see how these requirements might be fulfilled.